In this video, we're going to look at inverse functions. If we consider a function f, which maps each element x of the domain x onto its image y in the range y, i.e., in other words, f is such that it maps x onto y. So let's see what that actually means. So we've got our domain x and our codomain y, and each element, whether it's 1, 2, 3, is mapped onto each element ABC via some function f. Then we can say that f is such that it maps x onto y, and each element in x belongs to the real numbers, and each element in y also belongs to the real numbers. Then, if this is true, there exists an inverse function that will take us back the way, and that's going to be f to the minus 1. So it will map a onto 1, b onto 2, and c onto 3. Now there are some rules regarding inverse functions. A function only has an inverse if it's a 1-to-1. This is because if we go back the way, so if we've got a 1-to-1 going in the forwards direction, in the backwards directions it's also a 1-to-1. If we have a many-to-1, which is still a function, then the inverse of that would be a 1-to-many. And that goes against the definition of a function which maps onto one and only one. So whilst a many-to-1 is a function, a 1-to-many is not an inverse function because it maps onto more than one. We could in theory have a many-to-1 as an inverse of a 1-to-many, but because a 1-to-many is not a function, then the inverse function doesn't exist either. So it only happens if it's a 1-to-1 function. The second thing as well to note is that the range of the function will be the domain of the inverse. So if we look back to the example that we've already drawn out, x was our domain for the function f, and y was the range. Now if we're taking our values from y to x, then that means that c are the starting values, so that's going to be the domain, and the range of the inverse will be the x values. So what we have is that they switch. So the domain and the range of the function and the inverse switch with each other. And the inverse of a function is a reflection of the original function of the line y equals x. And we may have already seen that in certain things already, if we think to other graphs. What we can see here, this is a graph of a function and its inverse. And we've also got the line of y equals x drawn. So y equals x is the purple graph. Our f of x is this black graph, which kind of looks like a cubic, but it's actually to the power of a 5. And the red line is the inverse function. And we can see that they are reflections in the line y equals x. And we can change this function to y equals x squared. And we can see the black line is the quadratic graph, and the red graph is the inverse function because they're reflections in the line y equals x. The inverse, of course, of the x squared is the square root graph. So that's what we have now. In function notation, actually, the x squared graph is a many-to-one function. So this would be a 1-to-many. So there isn't an inverse here, technically. We have to do something different so that the true inverse exists. But hopefully you get the idea that a function, no matter what it is, to find its inverse, it will be a reflection graphically in the line y equals x. I'll just show you one more to prove that. So we've got the exponential graph, which we know tends towards 0 as x gets closer and closer to negative infinity. And as x gets bigger and bigger, it tends off to positive infinity. And we know the inverse of an exponential is the ln graph, and the red line should come to no surprise that that's the graph of ln x. And it passes through 0, 1, and it doesn't exist for negative values. And this is an example where an inverse function is perfect because this is a 1-to-1 function, so then the inverse function is also a 1-to-1. The basic method for the function, so if we had a function, now if it's written in f form, so if we had f was such that it mapped x onto x squared, we could say, well, let y equal x squared. Then if we let x to be the subject, so we could do x equals the square root of y, and then that's kind of our inverse function. So f to the minus 1 would be such that it maps x onto, instead of writing y, that was just something we introduced to make life easier, we'd write the square root of x. So in this first example, if we want to find the inverse of y equals 2x plus 3, what we need to do is make x the subject. So to do that, we'll do y minus 3 equals 2x, and then divide by 2. So y minus 3 over 2 equals x. So the inverse of the function is x equals y minus 3 over 2. And this equation was involving y and x, so it's okay to leave the answer in those terms. Example 2, g of x is equal to 5 over x minus 5. So if we let y equal 5 over x minus 5 and now make x the subject. So if we add 5 to both sides, we get y plus 5 equals 5 over x. Multiply up by the denominator, we've got x upon y plus 5 equals 5, and then divide through by the bracket, x equals 5 over y plus 5. So that means we've got x as the subject, so our g to the minus 1 of x is equal to 5 over, but instead of writing y, we'll write it as x plus 5. And that's because our inverse function is to do with x. We only brought in the y to make our life a little bit easier and more familiar. So because our inverse function is a function containing x, we need to replace the y with the x. We could do a numerical check for this. So if we did the g of, let's do 5, because that's a nice easy number, that's going to be 5 over 5 minus 5, which is 1 minus 5, which is minus 4. Now if we've done the inverse of g correctly, then if we substitute in minus 4 into the inverse function, we should get back to 5. So let's check that out. So g to the minus 1 of minus 4 is going to be 5 over minus 4 plus 5, which is 5 over 1, which is 5. So what we've got is 5 goes to minus 4 via g and comes back via the inverse. And example 3, h of x equals 10 minus x. Again, if we let y equal 10 minus x and make x the subject, we have y plus x equals 10, so x equals 10 minus y. So therefore h to the minus 1 of x, so the inverse function of h, is going to be 10 minus x. Again, we're dealing with the inverse of x, so therefore it has to be an equation in terms of x. Again, let's try a numerical value just to check that out. If we had the h of 17, that's going to be 10 minus 17, which is minus 7. So if we do the inverse of minus 7, we get 10 minus 7, which is 17. So 17 is mapped to minus 7 via h, and minus 7 is mapped back to 17 via the inverse function. Our next example, the function f is defined by f is such that it maps x onto x minus 1 over 2x plus 6, where x belongs to the real numbers and x is bigger than or equal to 1. So x could be 1, 1.2, 1.3, all the way up to infinity. So we need to state the range of this function. To do that, we can write that in a simpler form. So if we divide that out as a polynomial, so x minus 1 divided by 2x plus 6, 2x goes into x a half a time, and multiply that down, we get x plus 3. Subtract those, and we get a remainder of minus 4. So f is such that it maps x onto a half minus 4 over 2x plus 6, or a half minus 2 over x plus 3. Now when x is equal to 1, let's investigate what happens to the f of 1. And we'll see that's going to be a half minus 2 over 1 plus 3, which is a half minus a half. 1 plus 3 is 4, 2 over 4 is a half, which is 0. So when x equals 1, the f of 1 is 0. As x gets bigger to infinity, so we're okay with every other value from x bigger to infinity. It's going to work. We can multiply all of these numbers from 1 up to infinity by 2, and we can add those to 6, and we can correctly divide that into 4. So that's okay. So let's investigate what happens as x gets bigger. So what we'll have is that the f will tend to a half minus 2 over infinity plus 3, which is a half minus 2 over infinity. Now, 2 divided by an infinite number, that's going to tend to 0. So that's going to be a half minus 0, which is a half. So what we know is at the starting point, the value is 0, and as x increases, it's going to tend to, but never actually get to a half. So that means my range is going to be 0 is less than or equal to f, which is less than a half. And that's going to be the range of f. And it'll not equal a half because we'll never be able to get that far. Part 2 is find the inverse function, stating its domain and range. So to find the inverse function, what we need to do is let y equal x minus 1 over 2x plus 6. If we expand up or multiply up by the denominator, we're going to have 2x plus 6 times y equals x minus 1. Expanding out the brackets, 2xy plus 6y equals x minus 1, and we need to collect all the x's to one side. So we'll have 2xy minus x equals minus 6y minus 1. If we factorise out the x upon 2y minus 1 equals minus 6y minus 1. So x is going to equal minus 6y minus 1 over 2y minus 1. If we multiplied through by a minus, it would make it a little bit nicer as 6y plus 1 over 1 minus 2y. So that means the inverse function of f is such that it maps x onto 6x plus 1 over 1 minus 2x. Remember, we replace all the y's with an x. And what we're asked for is state the domain and the range. Now, in the last part of the example, for f, we knew that the domain was x was bigger than or equal to 1, and the range was 0 is less than or equal to f, which is less than or equal to a half. So that was going in this direction. The inverse function will map back the way, and we've now got an expression for the inverse function of f. So its domain is going to be the range of f. So the f to the minus 1, which we've said is 6x plus 1 over 1 minus 2x, that's only going to exist where x belongs to the real numbers, such that 0 is less than or equal to x, which is less than a half. So that's the domain. And the range is going to be f to the minus 1 belongs to the real numbers, such that f to the minus 1 is bigger than or equal to 1. So the range and the domain have switched positions. Example, given that f of x equals x minus 2 squared and x belongs to the real numbers, state a domain for which f of x can have an inverse. Find this inverse and state its range. Now what we have is that the f of x is a quadratic, and what we know is that x squared is always bigger than or equal to 0, and the minimum point occurs at 0, 0. If we have x minus 2 all squared, again is going to be bigger than or equal to 0, but the 0 value occurs when x equals 2. So the minimum value is 2, 0. that means our x minus 2 graph is going to be a quadratic graph which has a minimum point at 2. Now, we know, or we should know, that this is a many-to-one function. And for an inverse to occur, that means it can only be a one-to-one function. So what we need to do is restrict the domain so that the quadratic is a one-to-one function. And we want the biggest domain possible. So what we will do is we can look at half the graph. And we could look at either x being bigger than or equal to 2, bigger than or equal to 2, or x being less than or equal to 2. But generally we always like things more often than not positive, so we'll take the right-hand part of the graph. So by restricting the domain to x being bigger than or equal to 2, we're going to have a one-to-one function. So I'm going to write that as f of x equals x minus 2 squared, where x belongs to the real numbers and x must be bigger than or equal to 2. We've now got a one-to-one function. Now, to work out what the inverse function is, we're going to have y equals x minus 2 squared. Take the square root. We've got the square root of y equals x minus 2. So the square root of y plus 2 is equal to x. Now, what we might have, whenever we take the square root, technically we should be having a plus or minus y, but because this is a one-to-one function, and we've got positive values, so x being bigger than or equal to 2, being mapped onto positive values, we're only going to consider the positive square root of y in this case, because it's a one-to-one function. So x exists for positive x, so therefore we're going to have the positive square root of y in this case. So our inverse function then is going to be f to the minus 1 of x equals the square root of x plus 2. So we find the inverse, now we need to find its range. And the range of this function, the range of this is going to be the domain of the first one. If we think back to their basic function boxes, if we've got the domain being mapped to the range through f, where this is the domain and this is the range, inverse function will do the back the way. So the domain of the inverse function, is where we start, and that was the range, and the range of the inverse function will be the domain of f. So if we're asked for the range here, it's going to be this condition here, where f to the minus 1 is going to belong to the real numbers, and f to the minus 1 is bigger than or equal to 2.